All right, let's get going. So last time we talked about natural language processing, in particular translation, and we looked at sequence models first. So you have an input in one language, like I love coffee in English. There's an encoder piece of the network, which is shown in blue. And then really just one slice of latent states go across from that encoder to the decoder, which is in red. And then you start generating a translation. And in this example, it's showing you a sort of an n-best with n equal to 2 generation of two sequences of outputs. So we pointed out a number of limitations of that model, the main one being the fact that all of the semantics of the sentence is trying to squeeze across that boundary, which has fixed length. And in addition, perhaps informally, we argued that most of the time, at least for the translation task, the most relevant input for a particular output word is really just one word. And so if you did have attention, it would be close to an identity map, possibly with some permutation. And so we looked at the model from Bengio et al. From 2015, where they implemented something like that. Without too much detail, it used an actual learned matching function between the latent state of the recurrent network and an encoder, which was a bidirectional network. It matched those two latent states, and then from that, it computed the weight of the next state along the sequence of the input. So it was very complicated, and it had this up and down attention. So that was improved then by the work by Luong and Manning. But we pointed out, excuse me, also that while language translation is a canonical task, and it's an important one from one language to another, once you have a translation engine, it's really very general, and you can solve a variety of tasks with it, depending on what the output looks like. So you can take unstructured natural language and produce something much more structured, like a parse tree that's encoded as a different kind of sequence. So last time we introduced the transformer model, which is really the convolutional network for natural language, and it's really come to dominate almost all language tasks now. So a few different characteristics of it. It has this 3 types of attention now, whereas the other models really only had a cross attention. The transformer network has the cross attention, but also self attention on both encoder and decoder side. And it's that self attention that's replacing the recurrent information flow from the recurrent networks if they were doing encoding and decoding. And there's a few other elements of it too, the position encoding, which we'll talk about today. Also the multiple heads. So let's walk through it again. Walk through some of the core ideas, and then we'll talk about some elaborations of it. This is a little bit redundant, but it's a kind of complicated model, so it's important to have a good grasp of it, and it's also very important for assignment 3. So if you recall, the idea was we start off with a sequence of inputs, x1 through x4 here. And each input goes through 3 linear maps to produce both value key and query views of that input. And in each position, like in the second position here, the second query goes through as the query, and it's computed, it's sort of combined with inner products with all of the keys across that layer. And the inner products are turned into softmaxes so that the weights are normalized. And then those weights are applied finally to the values in the 4 positions. And because the softmax adds up to 1, it's a convex combination of those things. And usually it's attending mostly to one input. And that produces the output. And then there's a similar copy of that, all of that logic at each position in the transformer. So in fact, you have a quadratic amount of calculation going on. So hopefully that was clear. Yeah. Now, the representation of the models is actually simpler than that, because in practice, the query key and value vectors are actually bundled together as matrices. So the row index of the matrix is the sequence position index, and the column indices are just the latent dimensions. And so then we can actually write, I didn't even show you the full graph with a quadratic amount of calculations, but we can write all of what's happening as this single matrix formula here, where you do all of the query key inner products as a single matrix product, normalize them according to the length of the keys, just number of dimensions in each key, and take the softmax and then apply it as weights to the values. And alternatively, it's shown as a computation graph on the right side. And we'll talk about the masking part in a moment. And again, to review, the standard attention is just like a one-dimensional attention, what we just looked at. We assumed that there was a single weight being applied to each value. But it's very beneficial for most applications to actually have multiple heads. So different, I guess, different views of the data that perform different semantic tasks, even at each level. So all you have to do to implement that is basically split the V, Q, and K vectors, let's take them as a vector now, into ranges of values and treat each range of values as a different head, and then only compute the matrix operation from the previous slide to that block of data. And it ends up, the matrix operations, instead of being standard matrix operations, they become diagonal blocked operations, and there's already routines that do that in any neural network package. So doing this is just actually, it's the same formula as before, in fact, but you pass different parameters to the matrix product to get it to do this operation. Okay, so also we looked at the transformer encoder, and it had a few characteristics. The input comes in, it's the projection matrices are applied to produce queries, keys, and values, and then the multi-headed attention is provided. But in addition, the value before it's split is passed through as a residual, similar to ResNets, so that this whole column of sequence calculation really always has a copy of its base input being passed through, even if that, as we pointed out last time, that unit of encoder is stacked vertically a fixed number of times. And yeah, so that way you kind of don't lose track of what your original input was. And then there's some normalization in there, which is layer norm. Okay. And also we looked at the basic encoder-decoder. The decoder is a little bit more complicated because it's got both self-attention to the output and also cross-attention to the input. The cross-attention, pulls queries from the output side, but retrieves keys and values from the input side, right? Well, it does. Okay, so, and abstractly, I think we also showed this picture. Perhaps it's a little bit tricky to digest. So let's actually drill down and look at what this looks like, maybe just one step more explicitly. So let's just look at encoding on the encoding side. So there's an input sequence. Some words go in the bottom, and I'm assuming those words are represented already as embeddings, like with word2vec or something. So already these are vectors of some dimension that equals the basic latent dimension of the transformer. And then actually, there will end up being two different types of unit. At the bottom layer, that's normally where position encoding is being applied. So this TEP unit has both the transformer encoder and also the position encoding at the bottom. okay? Past the first layer, you have only the transformer part here, okay? So because the position encoding at the bottom is being residually passed up, so even up here, you get a sort of a residual copy of the position encoding from the bottom. So that each, well, you get both a copy of the input being passed up residually and also the position encoding of that input, where that lies in a sequence. Okay, and yeah, the multi-headed attention has the effect of producing, this is self-attention, so there are weights between every word and every other word. A lot of the time it's diagonal, but there are certain other traits. Like in my opinion, my has got strong links to the opinion that because it's like, what is that, adjective? Yeah, it's adjective, I think. And also in is part of a phrase, so those are closely tied together. But then particular heads focus on different aspects of the input. So this one, it's application. So this is anaphora. Anaphora means references. So when you use a word like it or that, it refers to a specific thing. So its application, the it is the law in this context, and the application is, well, effectively it's sort of like, I don't know if it's actually an adjective, but it's modifying this word application. So there are two strong weights whenever you have anaphora between the reference and the thing it's referring to, and also typically, well, if it's being applied to another thing, then you have strong weight there as well. Yeah, and you can have many different heads in general. Here you've got a phrase, making the resonate. So this is a verb phrase. The verb phrase is making more difficult. That defines, in a sense, a single action that takes multiple words to describe. So all of those words are closely coupled with attention from several heads. It's not completely clear what the heads are doing, but you probably get a gist of what they're doing. Okay, so that's self-attention. Any questions so far? So now let's look a little bit more at decoding. So this is going to probably still be a little bit confusing because as I've just argued earlier, on the encoding side, although there are conceptually different word positions and different columns of the transformer, the implementation is really just a single sequence of nodes in a network, because each sequence, any particular latent vector in the sequence is actually encoded as a matrix with the sequence position as the row index. So you never actually see all these unrolled units. You only see effectively one unit. However, when you're actually generating on the output side, that's not true anymore, because in order to generate text on the output side, the decoder generates one word at a time, just as the recurrent networks do. So when you're generating, you have to start with the first row of decoders and generate one word somehow, either sampling or n-best or best. So I've removed the self-attention here, but we still have all these input units. So on the output side, though, we have two lots of attention, right? We have the multi-headed self-attention, which I'm showing in green, going down. And we also have the multi-headed cross-attention, which I'm showing going across. So I have two types of attention. I'm for now ignoring the different heads of attention, but they're still there, right? So even though I'm only showing blue cross-attention arrows, there are actually multiple heads of cross-attention, and there's multiple heads of self-attention, right? We're just focusing on one thing at a time. But hopefully this picture is intuitive and making sense. The cross attention starts off effectively going to the input. As you go up, it starts going to the various layers of the input encoder. And then finally at the top, at the output, see there's a softmax, a linear layer and a softmax to match dimensions. So on the output side, you generate probability distribution over the vocabulary, as we did with sequence models, and you can sample from it. All right, does that make sense? All right, so in one step, we might generate one word. We're trying to translate this English sentence or phrase into French. So we generate one word, which is the word for fox. And okay, so just as we did with recurrent networks, now we have a word which becomes the input to the next layer of the output decoder. All right, so similar to before, each unit in the next column has cross attention back to the input words or the intermediate layers of the encoder, and it also has self-attention, which means self-attention means attention to the output side. But notice, so what do you notice about the green arrows, though, as opposed to the blue arrows? Anything? Actually, they're actually different, but perhaps, actually in a non-obvious way. So, well, anyway, obviously the blue arrows go to the left. The green arrows, though, also can only go down or to the left. So in other words, I can't attend on the output side to something in the sequence to my right, because if I did that, I wouldn't be able to use this as an autoregressive generator. Autoregressive means uses its own output as an input. So my green arrows can only look back, or look in the current column or to the left of what I've already generated. I mean, that's a choice, right? I always want to be able to generate new tokens by only looking to the left. Okay, so, but we do exactly the same thing we did with recurrent sequence models in terms of taking each output token and feeding it as the input to the next column and generating one word ahead from there. But what, because we have flexible attention, whereas in English the noun comes at the end here in this phrase, in French it comes first. And so you can see, intuitively you would expect the cross attention, the blue arrows, to be attending to the corresponding word to the output. So they're actually going to go backwards. Well, the green arrows attend to the previous state. It's a little bit harder to say perhaps what they attend to, but clearly Brun is strongly related to Renard because it's the color and it's modifying the noun. So there's likely to be strong attention going that way. So in one more step now, so now I've just left aside the cross attention to again make the picture a bit more interpretable. And after generating the word brun, which is brown, I feed that back into the third column and generate the final word, which would be rapide. And again, I'm just doing the same operation each time, but now you can see perhaps even more clearly that we have this causal attention on the output side. The green attention is causal, meaning it can only go back in time. And it's also called masked self-attention for that reason. Okay, so are we clear, how this works at generation time? Okay. At training time, though, so imagine this is essentially what I want to train. At training time, I actually have this phrase, and I would stick, I'd have a stop symbol, no, one more column with a stop symbol. But I have this phrase, and I have this input. So in fact, I have the entire state of the output. And so during training, I don't actually have to go sequentially. The dependencies in the output are only going up. So everything I need to compute this layer here is available, including these inputs and these inputs. So in other words, I can do this in parallel again. So in other words, I can use a matrix representation for all of the vectors in here and all of the vectors here. Even though I'm copying this down, in training I don't have to, so everything's available. So once again, the transformer's lack of recurrence means that it's much more parallelizable. And so I can just basically do this. So if you recall, the earlier picture that showed just the encoder and just the decoder, that's really all I'm going to implement for training. With the one caveat that I have to be careful that these weights are actually causal. And that's a simple matrix. It is a masking operation. If you think of it, you basically take a triangular mask and multiply that by it's a little, the actual implementation is a little tricky because you want to do that before the softmax. And you actually mask the real values and set the other masked values to minus infinity, because if you set them to 0, you'd actually get a big softmax on the output. But anyway, so is it pretty intuitive how you could do that? Like basically, because of the matrix representation, if you remember the matrix equation, it's Q key transpose, or Q transpose key. That's a matrix. The ijth value in that matrix is the attention between column I and column J. And causality just means I is greater than J. So in other words, it's a triangular. So you can make a simple triangular mask that causes the attention only to go down or to the left. All right, so that's really that's really it for the complete picture of the transformer. I think if you can grasp that, you're in good shape to use it. Excuse me. All right, and a variety of other things pretty much stay the same as before. You can still do n-best decoding. Now, once again, we're on the generation side, so we're going one column at a time. We still have softmax outputs, which means we get a probability distribution over the vocabulary. And so we can sample or we can use an n-best strategy. If you remember how we did this with the sequence models, we essentially have one column first, and then we have k copies of the second column, which are independent of each other given the first column. And you can get different continuations of each word that's generated in the first column. So let's say it's say Renard, which is fox. You feed Renard in, still using the context from the first column, and you might get those two words which mean brown and green with those probabilities. Or if it guesses canard, which means duck, and you generate from canard, you might get these words as the softmax output. Guess the duck is yellow versus blue. But if you compute the product of the probabilities, you find that the best two options are Renard Brun and Renard Ver, and so there. And then so the third column would actually be based on only the second column here. But it would continue from that. But hopefully this is really the same, almost exactly the same structure as what we did with sequence models, except that we're using transformer output stages autoregressively. So we good with that? All right. So now we get to positioning encoding, which is actually kind of an interesting and rich problem, which is really glossed over in the original paper, because I think in the original paper it was a total hack that worked, and they don't give much justification for it. But it has very interesting properties, actually. So the idea here is, in addition to having the input, right, you have input words. The model, a priori, because of all the symmetry between keys and values and positions, it has no sense of order or position a priori. In particular, if you took a transformer model without position encoding, and you take any sentence on the encoder side, it wouldn't matter on the decoder side too, take any sentence or sequence of words, and then generate an output, and then randomly permute the input sentence, then the output has to be a random permutation of the same random permutation. So in other words, if you permute the input, the output would permute because there's no sense of position. So in particular, that means it's basically a bag of words model. The output's determined only by the set of words, not really by their positions. So that's not what we want, right? We know when words are close together, that matters. So we have to somehow inject into the network some knowledge of where things are. Yeah, basically, the position encoding is also a matrix. And so if you think of position along the input, along the x-axis here, the position encoding is a function with two inputs. The first one is the position x, and the second one is just the component. The position encoding is a vector, and k means it's the kth component of that vector. And it turns out to be sinusoids and cosines of different frequencies, and that means that each color here encodes a different dimension. So k is, this is k equals 1 here, say, this is k equals 2. It's actually 4, 5, and 6, and 7, but, anyway, each of the curves corresponds to a particular dimension of the encoding. Is that making sense? I haven't yet said what the frequencies are, but hopefully we're at least clear what this is representing. So here, it's probably a 7 or 8 dimensional encoding, and they just happen to be showing you 4 dimensions, 4, 5, and 7, 6, and 7. Yeah.
And what do you mean by dimension?
I just mean that maybe component, or so concretely, let's say I have that my encoding is going to be have dimension 8. The dimension is going to match the dimension of the embedding, because I'm just going to add them together. So typically it's going to be 1,000 or something. But let's make it be 8 for simplicity. That means I have 8 different values to fill in a position encoding at a particular point. And each one of them is going to be a sinusoidal function of the position with a different frequency. In fact, we'll always have cos and sine of every given frequency that we use. So k is just the position in the vector encoding, or they call it dimension. All right, so in other words, and explicitly this is what it is. So the normal encoding in the even positions of the encoding. So again, k is just that particular coordinate of the encoding. If that coordinate is even, we use a sign with this frequency that's a function of the position. I mean, it should be, otherwise it'd be the same. There would be no point. But basically it's x. So it's a fairly low frequency. It's x divided by this fractional power. D is the actual number of components in the encoding, which would be typically 1,000, the same as the embedding. So D might be 1,000. 2i then, it's just the different values as you go through the vector. So in other words, the frequencies are a geometric series. Excuse me. And the odd ones are just the matching cosines of the signs. Now, this turns out it has a lot of nice properties. They really don't give much justification in the paper. But it does a few different things. If I have a position encoding, if you remember some of the identities for sine and cosine. So first of all, how do I change position? If I have sine and cosine of something with the same frequency, changing position effectively means changing phase. So, and when you want to change phase, the sine cosine, the changed phase formula, you do sine cos plus cos sine, which means the changed phase is a linear combination of the original sines and cosines. So I can do little 2x2 matrix multiplies. If I learn them, I can basically shift left and right in any coordinate of the position encoding by given phase. And in fact, if I choose the different phases carefully, I can, in every coordinate, actually move right in a consistent way. Like, if I have two frequencies and one's twice the other, I want to move a particular displacement in x, then I can move by sort of theta for the higher frequency. No, I can move by theta for the lower frequency and then 2 theta for the higher frequency. In other words, with this encoding, I can apply linear functions to the encoding to move left or right, which is kind of by a fixed amount, which is obviously helpful because if I want to look at the next word or the word 3 positions away, the attention heads can learn to do that. So that's one thing. With this system, it has learnable offsets. Another interesting property is when I take the inner product, if I want to compare two positions, the inner product depends only on the distance between them, not their absolute positions. So if you plot this, how similar, this is also a measure of how similar the encodings are, right? If you take inner product at the exact position of self, the inner product's maximum. In fact, it's basically, well, it turns out to be d over 2 because you get sine squared plus cos squared, which is 1 for each pair. So there's d over 2 pairs. So it ends up being, for 1,000 dimensions, it's 512 if you look closely. So if 0 is the displacement between the two keys, two position encodings, it just decays away as y minus x increases like this. So you can learn displacements. Also, a priori, it strongly favors, it'll give you high inner products, which means you're likely to retrieve values from keys which are close. Is that making sense? Yeah. Which one? D is the dimension, so of the encoding model. So it's typically 1,000. It's 1,000 here.
What about
I is an index that's indexing from 0 to d over 2.
I is between 1 and k.
No, k is just in this example, k is 2i or 2i plus 1. Or if you want, you can also replace 2i with k, and just have a condition that k is even or odd. They're just sort of synonyms. It's just a little simpler if it's I, but yeah, k would work as well.
I and 2i plus 1 are just odd and even.
I are like, when you write this, I is the for loop variable, and I ranges from 0 to d over 2, roughly. Actually, I don't think it's not 0. You don't want constants. It goes from 1. So anyway, yeah, so this is exact if you get exactly the same inner products for every x. So, excuse me. Among them, perhaps unpacking the mysteries of why this is what it is, the formula that's used in the paper seems to be purely empirical, and they don't give any more justification than it worked. Interestingly, if you change the formula around, in particular, invert the role of, turn I from, instead of being the exponent, you turn it instead into the base with a fixed exponent. In other words, make it a polynomial. And use this peculiar value of 0.883, you get something that has obvious meaning, which is that this plot now captures, fairly closely anyway, the incremental mutual information between those two positions if it's natural language English text. So natural language English text, we understand it really pretty well. And we know that the information in a text of length L grows as L to that power. And that power, there's lots of empirical work on this, so we know that power pretty accurately. And simply from knowing this, you can actually compute how much information should flow between two positions in essentially how much information one word gives you about the other word. So if you compute that, you have to kind of take a derivative, but you find that actually there's another step. Once you know how much information should flow, you basically know what the weight should be between two positions. Once you know what the weight should be, you can invert from the weight, the weight function, back to the frequency of the sinusoids and cosines. So you do those steps, and then you find that that the function that you get from doing that is almost identical to the empirical function out to about word position 6 or 7. And then out in the tail, they start diverging. But if you actually try this function, it works at least as well in most cases. And at least you can justify this a bit better. OK, so we clear so far? Yeah, and the last thing that position encoding does is that the encoding has different frequencies. So, and you can move left or right by a fixed distance. But your model can learn either, it can learn to use all of the frequencies or maybe just the lower frequencies. So in other words, you can easily learn fuzzy ranges of position or fuzzy displacements. And that's pretty useful, right, if you know that you expect an adjective maybe to have, to be separated by some words, intermediate words from the noun to which it refers. You can kind of guess a fuzzy envelope of where the actual noun might be. So it allows you also to learn distributions of displacement of position to find things. OK. So when the first transformer paper came out, they got some pretty nice improvements. Maybe not always exactly state of the art, but generally, usually they did very well in terms of computational effort. So you can see on English-French, they were very close to the previous state of the art, but they did so with about a third of the compute. Wait a minute, where are we? No, a tiny fraction of the compute, about a 50th of the compute effort went into that model. And let's see. Sorry, it's too many things. So in German, which is considered a more difficult task, they went well beyond the state of the art. OK, so I think that's right, isn't it? Yeah. All right, so, but subsequent to that work, people, that was one group of authors. Lots of other groups of authors started experimenting with the model, and really it kind of took off in there and left everything else behind. All right, so, OK, so having talked about the basic model, let's discuss some of the particular challenges and practical issues with getting it to work, unless there's any questions more about the model. Okay, so we've so far assumed that we have a fixed vocabulary, and well, a whole lot of problems with that. Language evolution, misspellings, weird punctuation, people putting asterisks or underscores or other random characters, hashtags around words. So in practice, your real vocabulary in terms of strings of ASCII characters is typically huge. So, let's pick an example of a recent kind of new word like styleliner, which would often be outside of the scope of a particular vocabulary. So the first option to dealing with this is to just have an unknown character. And then unknown kind of assumes all of the semantics of all of the words that are not in the current vocabulary. So obviously that's not very good. And also in practice, if you have something like a 30,000 word vocabulary for any kind of interesting task or Wikipedia or something, the size of unknown ends up being pretty huge, like 20% of all words or something will end up being unknown. So a lot of semantics of the text is being lost. So, yeah, well, and the second solution was make the vocabulary bigger. And so people started doing that for a while, but obviously, so we didn't talk very precisely about this, but if you try running the transformer models that we've been running so far, it's pretty easy for that very last linear multiplication and softmax to dominate the running time, because the effort to do the softmax is linear in the vocabulary size. Everything else is around 1,000, and you have 50,000 to 200,000. So big vocabularies can end up dominating the whole pipeline. Yeah, but beyond that, the model also has to see these very sparse words enough times to figure out what they mean. And yeah, you still have, and because of the power law structure of natural language, realistically, instead, unknown might go from 20% to 15% with that transition from 50K to 200K. All right, so a better solution is to stop treating those big words, well, unusual words, as atoms, and instead treat them as compositions. So now we're going to break that particular word. The regular words stay in the vocabulary, but the composite word gets broken into a kind of base word plus a continuation with special characters to indicate that it's a continuation. So we use here, it's hash to mean a suffix, basically. So, and it's obvious, you can always parse back from this sort of representation back to an actual sequence of words, because whenever you see this, it gets stuck to the previous word, and remove the hashes. So this is called word piece tokenization, and a particular implementation of it is byte pair encoding. It's a little bit like Huffman encoding. You kind of optimally figure out what this should be, and roughly speaking, you take a vocabulary of maybe 32,000 words. Maybe the top 20,000 words go straight into the vocabulary, and the rest of the dictionary is just enough sequences to cover just about anything. If you think about it, you only need, about 900 tokens to cover all word pairs. So if you have hash two letters, you've sort of got almost everything. And you just have to do those two word pairs. But it's cleverer than that, and it instead covers more frequent sequences of letters that are longer and so on. So it turns out to be very efficient. So is that clear? Yeah.
How do you know where to separate them? Like Starliner? How do you know to
Well, that's part of the algorithm. Yeah, it's optimized to kind of maximize the probabilities of the tokens that it uses. So star is already high probability.
so it's seen star before, so that you recognize it?
Yeah, it's well, it has a choice, right? I mean, it could do Starliner, or it could do STA, Erliner. The Erliner is not very likely to be reused by other tokenizations. But liner is a common suffix and star is a common word. So this would be more probable. You want it to be probable because you want each word that you put in the dictionary to consume a lot of probability, because that means the encoding will be shorter. Yeah? Sorry, the back first.
What about like short misspelled words?
Well, they actually are in there. You know, you'll... Well, I gave an example of a universal encoding, which is I just encode all two-letter sequences with a hash suffix. So then I can, you can fit 3 or 4, I think, without even being clever. But typically you would sort of do something a bit more clever, which is look at the actual frequency of occurrence, and then of the longer ones, and then put some of the longer ones in there so that you're always trying to reduce the length of the encoding for efficiency reasons. But even if you do it in a completely dumb way, you could do, let's see, I think, yeah, but you can always do 2, you might be able to even fit 3 length, all sequences of 3 letters in a vocabulary of about 30,000. And that's typically what people are using. So you still look confused.
By length of the encoding, do you mean it's like all
Oh, I mean how many tokens it takes you. Because your complexity, the complexity of everything is a function of how many tokens there are in the sequences after you've done this. So you want to minimize that. But it's more than that. You also, in terms of a model, the higher probability the tokens are, the better it can learn, right? Because the more times it sees that token, the more times it kind of gets data about what that means. Yeah, you have a question?
So, so the model that splits, for example, Starliner or any other word and tries to split up the word into different pieces, that itself must be a pretty complex learning model too, right?
Actually, I'm not sure if it's really even learned versus just statistically driven. I honestly, I'm not sure it's not similar to Huffman coding, where you just basically maintain frequency tables for sequences and then optimally walk through a tree. I'm not sure, but I don't see that it has to be learned necessarily. Okay, so it is kind of a black box that people don't usually look into, because I think it's a solved problem in terms of that optimization. Okay, so some advantages and limitations. Advantages are that, we keep the vocabulary manageable. At 30,000, the cost of the softmax on the output is reasonable. It's less than typically than the overall cost of the layers below. There are actually no more unknown tokens. Everything now is meaningful, and although Starliner really is a novel word, it does inherit some semantics from the notion of star and liner, right? It's a liner is a big passenger craft, star is it's up in the air, and so on. So you can have multilingual work. Yeah, you can actually mix together multiple languages, which is relevant in some cases. And the subword units, as I just said, have some meaning. Yeah, and well, this is almost like stemming. Also, you can implement stemming strategies as word piece encodings. Limitations. Yeah, sometimes things grow, but if it's a well-optimized encoding, you'll find that it really is remarkably efficient. Like, you can often shrink from a vocabulary of hundreds of thousands of words down to, say, 30,000 and only increase the actual length of sequences a few %. at the same time eliminating all the unknowns. I see. This, oh, I see. Well, yeah, all right. So there's some ambiguity in the encoding. Yeah. Tokenization is actually, I'm not sure that means it's not uniquely reversible. It's not true it's not reversible, but anyway, it's not unique. Anyway, so they're more or less universal with transformer models these days. Okay, so let's look at one kind of motivating example of using translation in a different way. So, yeah, so for summarization, all right, actually I want to move on. Yeah, we want to do large-scale summarization. I actually kind of want to ask you about what's on that previous slide. So let's go straight ahead. So let's suppose we have something like Wikipedia. So we want to do summarization. So the input is an entire article, and the output's going to be a summary. So the input has length n, and the output summary, which is shorter, has length m. So what should be the complexity? This is a clicker question. If you click it. So what should be the complexity of the attention? Complexity being how many links of attention are there? How many operations in the calculation are there? We get one more reply. We've only got 2 so far. All right, now we got 4. Okay, great. All right. Oh, interesting. So we have 2. Well, we actually have a lot of divergence. Now what's winning now? B. Interesting. All right. Okay. Well, let's. All right, well, I don't think anyone liked A. Let's look at B. No, the problem is that basically the 3 terms are the self-attention on the input, the self-attention on the output, and the cross-attention. But the self-attention is all-to-all, and it's a matrix multiply. Actually, matrix multiply, it's actually I should have been careful about attention, but anyway. No, it's quadratic, actually. Because remember, it's all-to-all, right? It's actually cubic if we count the operations. I shouldn't have said operations and links. The number of links is quadratic, right? Because remember, you have an attention link from position I to position J on the input side, right? And that's actually computed as an inner product. No, actually, I'm sorry. This is correct as a function of input length and output length. It's also multiplied by the dimension of the network, but asymptotically, that's a constant here. So anyway, so that's not right. Come on. So the third answer is right because, the self-attention on the input side n is quadratic. We explicitly compute a weight between every I and J position on the input. And we do the same on the output, so it's m squared on the output. And we have links from every output position to every input position, so we also have that third term. Oops, come on. All right, so because we have an n squared term, well, we would have if we had an encoder, the summarization model actually dispenses with the encoder. And it just has a decoder. And to make that work, instead of self-attention, instead of the cross-attention going into an encoder, it goes straight to the input words instead. You can still do the multiple layers of output. It's just that every cross-attention layer collapses onto the input words. So then the complexity, we lose that huge term, which is quadratic in these very long sentences. We still have a pretty big O of n term for the cross-attention, This is still pretty big, but at least we've lost, oh shoot, I mixed n. Sorry about that, this n and m is not consistent between the two. This is the n squared term. This should be m squared. Anyway, you hopefully get the idea. The input attention is the most expensive term here. Yeah?
Well,
Oh.
encoder is like you're training, right? You're training
You're training both of them at the same time. You're still training the decoder. When you have, because you have you train this model, you would train it if it's trained for summarization on examples of summaries. So you still have them on the output side as well. You know, on the output side, you just, displace the word by 1 to make the input and output supervised values. Yeah, and here are some comparisons of the transformer model with various other models. And you can see that, let's see, here's various, yeah. So with that explanation, here are some of the bells and whistles that they add. And you can see the transformer models getting lower and lower perplexity. Perplexity is the log, the average. Perplexity is the exponential of the expected log probability. So it's an average across the softmax of the output. And if you like, it's the branching factor but from one word to the next. So an average, if it's 2, it means that from one word to the next, you have roughly 2 choices. It's not exactly 2 because there's k choices, but some of them are less likely. So the number of bits is 1 bit to determine what comes next. But anyway, lower perplexity is generally an indication that the model's fitting the data better. And the Rouge score is a variation of blur that we looked at, which we looked at last time. And you can see the blur scores are now matching the generated summaries to the human summaries are really getting much better and in the high 30s compared to only about 12 for a sequence-to-sequence model. So, is that clear? Okay. All right. So I'm actually getting a little bit ahead here, which I don't want to do because we're going to discuss, well, I'll do some of this, but I think mostly we want to focus on these heavily pre-trained models next time. Anyway, so we've already seen these very interesting relation as algebra models where you can look at the displacements between pairs of words in a semantic space and infer that the vector behaves like a relation. And so you can do algebra. If you subtract woman from man, you can add that vector to king and get queen as the closest point in the space. So let's see. And similarly, in going from an RNN to a transformer, you're basically taking away the recurrent attention and replacing it with self-attention between distinct layers. So there's a very powerful recurrent language model called Elmo, and it's named after the character, which was about a year later largely displaced by a model called BERT, which is bidirectional encoder representations from transformers. And roughly speaking, it's the same arrow as goes from here to here. So we'll talk a little bit about these two models. A very interesting difference between natural language text and image understanding is that with image understanding, you can argue that captioning or classification of images is kind of a universal task. At least in the early days, people trained AlexNet models to do ImageNet classification, and then they found that they could use the inner layers of those networks for all kinds of other tasks. So, and it gets even better if you have fine-grained descriptions of the objects in the image and the relations. So with natural language, it's arguably even more interesting in that you can argue that natural language is self-labeling, in that it's already a description of something, and natural language is a symbol system that's been optimized for communication. So a sentence is both a sequence of tokens and also arguably a caption that describes what's happening in the sentence, if you want to think of it that way. So the remarkable success of the pre-trained model line of work, which we're getting into, is that you can just take massive corpora of text with nothing else, with no explicit labels, and do various internal prediction tasks, like predicting the next word from the previous words, or even taking out a chunk of a subsequence of some words and filling it in from both sides. And the model that you learn seems to be essentially universal as an understanding model of what's in the text. So kind of like the near universal power of labeled images, it's sort of the analogous thing is that there's a near universal power of self-labeled text. In other words, just text. And the more text you throw in to these models, the better they get at almost any natural language task. And the only thing you have to do, just as with ImageNet models, AlexNet models or the other CNNs, is maybe in the last couple of layers, take your pre-trained model and fine-tune for a particular task. Okay, so that's the general architecture. Yeah, and there are a couple of models now. BERT is the earlier one, and now there's a model from Google, which is called GPT. The difference is this one's generative as well as supporting kind of label tasks. Okay. Now, a lot of these models are called language models, which means that they are effectively generative models of language. So they assign a probability to any sequence of words in natural language. And in fact, you can use them to generate text. Yeah. BERT is a little limited in generative capacity, but it can evaluate sequences. Yeah. So anyway, and in fact, here's a conceptual picture of the three popular models right now. Actually, only two of them are popular right now. BERT, which is an encoder, a transformer encoder-based model. And OpenAI GPT, which is, I'm sorry, OpenAI, I said Google. OpenAI GPT, which is a decoder model. Why is it a decoder model? How can you tell that's yeah?
Because there's only connections going up and
Yeah, the connections are causal. So there's no connections forward from any word, which means you can, easily run this as a generator by taking the output, making sure the output is a softmax over the vocabulary, and then feeding back words you can generate. BERT, because it has bidirectional attention, is not directly generative. So Elmo is an earlier model, slightly earlier. These things all came out pretty close together, which used, as we have seen a number of times, bidirectional LSTMs allow information to flow both ways on a text. And because of that, like BERT, it's encoder-only model. But anyway, the high-level idea is with any of these models, you have some input sequence and some kind of unsupervised training task, such as predicting a missing word, that you use to train up the model. And then you do a very limited amount of fine-tuning or training on a specific natural language task, like entailment or maybe question answering even. And the models do incredibly well. And they get better the more pre-training you do with them. Okay, so, and again, only so far GPT is generative because it's got causal connections in it. Yeah, so in fact, yeah, the generative model, GPT, is even a bit simpler than the normal transformer decoder stage because there's no encoder. You don't need any cross attention. So this is actually the an example column of GPT, and basically you have the pre-training task, which is just typically predicting the next character, and then you have an additional output that you then train subsequently, but you're already, everything inside the network has been pre-trained for the language modeling task. Okay, so if we delete all the pieces we don't need from the transformer, we end up with this, which is just the masked or causal self-attention to the output, and the kind of nonlinear layers on the output and the residual connections. And then position encoding on the first layer. And, just to reiterate how information flows, the queries are flowing up straight up always for the current position. The values and keys, though, can come from any position, but because it's causal, they will come from the left. Well, actually, you can have key and value from the current position as well. All right. So, yeah, and GPT is the simplest one to describe, and it's simply optimizing the probability of a next word given some number of previous words. And it's a parameterized model, meaning, neural network weights parameterized by theta. And then for specific tasks, we train a custom linear layer and retrain it. And we may or may not actually retrain all of the rest of the weights. If the rest of the weights are being retrained, it's done in a fine-tuning way where you train them much more slowly than the output weights. Oh, and the language modeling loss is typically retained, during the task-specific training. So it's actually multitask learning in that period. Actually, that's a bit of a challenge. Truthfully, people don't do that all the time because very few organizations such as Google or OpenAI actually have many billion-word data sets on which you can do language model training at scale. So in practice, it's kind of hard to actually keep training the language modeling task at full scale. It's actually it's more common that people take a giant pre-trained model and then fine-tune it only without adjusting the core weights. So some of the tasks that you can apply GPT and Elmo to include classification, where you run an input sequence through the transformer and just generate a single output at the last sequence position, which is the final class. Entailment. The idea with entailment, if you recall, is that you try to decide if two sentences are semantically related in some way. Entailment means A entails B or roughly implies B. Also, A and B can contradict. And the normal entailment problem is to take the two sequences and then output the kind of relation that they have, either entailment or contradiction or independent. So as a transformer model, you basically encode the two sequences with special delimiters between them. Otherwise, in all cases, it's just a sequence of words. And then you train the model, sorry, you have the pre-trained model in green, and then you fine-tune a small output stage with maybe 3 labels, again, right at the end of the output stage, the last column of the transformer to produce the desired entailment label. Okay. Well, another kind of Siamese version of that is to run, 2 different texts. Here, there's symmetry breaking happening. They're actually removing biases of the model when one text comes before the other text. So you run both orders of the model through transformers and then add them up to produce a result that goes into the linear layer. And then, let's see, so finally, multiple choice answers. You could have context, which is basically a passage that's supposed to contain an answer. Again, with delimiters separating it from 3 possible answers. Run each of these through a transformer, and that will give you a score of the answer the answer being in the context passage or not. And then, presumably, the one that gives you the highest score contains the answer. And with a little bit more work, you can actually typically find, train some pointers back into the passage to identify the text that contains the answer. Okay. Yeah, so GPT does extremely well on some of the tasks. So as the transformer models improved, they really started running away from other approaches. And the running away was in part because the performance kept improving with the size of the language model and the size of the training data and the number of hours. So you can see here they're already, I don't know, a couple of points better than previous models. And typically a couple of points improvement from 80% accuracy is really pretty huge. So, and with very little effort on the fine-tuning task itself. And let's see. Well, here are a couple of other tasks. I want to actually stop some pretty soon because a lot of the stuff is going to be covered next time. But to give you an idea, here are some other high school and middle school kind of general knowledge or what's the word again? Interpretation type questions, comprehension type questions that various models have been tried at before in the fine-tuned language model version, transformer-based version, really does much better on a number of those tasks, most or all of them. Actually, all of them in this case. Okay, so again, especially as you get into tasks that are more like general knowledge, even knowledge of science or basic current affairs or something, having these massive training data sets that really contain all kinds of current news and Wikipedia articles means that these models really have kind of arguably a fair amount of knowledge in them. So you can query them with even fairly modest context passages of text, and they can extrapolate it and pull in world knowledge and really, in many cases, hammer previous models that don't have that kind of ability. All right. Okay. Definitely we'll do this one next time. GP22 is, if you recall, I don't know if you noticed, but that was the model that came out maybe about 2 years ago that initially OpenAI declined to release because they thought it was too dangerous in terms of easily giving people a tool to create fake news. Because with very little, I guess depth 48, that one is the one that was originally released, and they subsequently released the other one. But it was able to automatically generate complete news stories that had many layers of structure that matched real news articles. So they'd have, sort of teaser lines in the beginning, but they'd invent characters in their roles as spokespeople. They would make statements, and they would close with kind of closing type remarks that news stories would typically do. So they'd learn content, they'd have consistent semantics of the underlying story, and they'd have the editorial structure of real news articles. And this is even not one of the most compelling ones. But, in order to get to that level of kind of understanding, the depth is pretty high. So this is a depth 48 model, 48 layers of transformers stacked on each other. But intuitively, it is really a question of deep understanding. The higher layers presumably are looking at these more global structures, and the lower layers are looking at actual, just well-formed language, consistent names and punctuation and so on, quote structure, consistent attributions and so on. So anyway, it does seem to be a very powerful general knowledge, the general model for understanding what's happening in a text. So we'll talk about this and BERT in some more detail next time. So I'll just close with the summary. All right, so mostly today actually we got into the more of the mechanics of transformers, how they use position encoding, just how the basic attentions work, first of all, how they use position encoding to do really quite a bit of work in terms of, since you lose the locality that you had with sequence models, the position encoding puts it back in rich ways where you can look to the left or right, and you automatically attend more to things that are nearby in a principled way. But otherwise it gives you, arguably a richer, more general alternative to sequence models. We talked about then the tokenization challenge at the beginning of natural language processing, where you want to deal ideally with open vocabulary text, but still be very efficient in terms of how long your tokenized text should be. And we argued that word piece models are a good way of doing that. And we just started looking at pre-training. We looked really just at the GPT model, but the core insight is that if you're able to train deep transformer models with a lot of data, among the different layers and heads of the models that are trained in that way, purely for sort of language modeling type tasks or generative tasks, you're able to get very rich semantics into the model, so much so that even very small amounts of later fine-tuning end up giving you state-of-the-art or better than state-of-the-art performance. Yeah, so we'll talk about more of that stuff on Tuesday. In fact, Philippe will cover Tuesday's lecture since he's more in this space than me. All right, we'll see you then.